Hello and welcome YouTube. Mr. Robbins back here with yet another brand new exciting video, all math-based of course, and as always it is an honor and a privilege to be serving you today, as it is every day, here in my virtual classroom. Step on inside as we jump into the Chapter 1 review of the Big Ideas Math Integrated Math 3 textbook on everything regarding geometric modeling. We've only done 4 sections, and really that's all there was. So 4 sections: modeling with area, modeling with volume, cross sections of solids, and solids of revolution. Those 4 things intertwined together. 18 problems total in this review. If you want to download it below, check out the PDF in the description section and follow the timestamp for each respective problem. There are also timestamps for parts regarding each section that they kind of introduce a part. They say 1-1 on this stuff, and then they do examples or an example, and then we move on to the problem set. So check those ones out. I'm going to do these with you from the textbook. If you go ahead and take a look now, we will begin. After this one, anticipate another video on the Chapter 1 test and cumulative assessment. Okay, let's go ahead and take a look. I didn't get my pen ready here. Let's see if it's all set to go. Number 1 eventually. Okay, cool. All right, let's begin by taking a look at what they say regarding modeling with area, section 1.1. Here's that example portion I'm talking about. They give you an example. 210,000 people live in a circular region with a 4.5 mile radius. Find the population density in people per square mile. So density is number of people divided by area of land. We're going to work off that formula. And we have the number of people's population. We need area of land. Because they called it a circular region and they have this radius, they're going to use pi r squared to find that area. So pi times 4.5 squared is 20.25 pi. I'm glad that they didn't do any early rounding here, but there's the square mileage to begin with. They do that division, work out your calculator, and they round to the nearest person. So they can say, in kind of a way that makes sense, about 3,301 people per square mile is that density. And that's how density works, right? How many people can you pack within some sort of unit of area with that? At least population density. Volume density is going to be the same thing when we get to section 1.2. Let's take a look at our question, starting with number 1. About 1.75 million people live in a circular region with 15-mile diameter. Find the population density in people per square mile. So it's the exact same kind of question as the example 1, which is always nice to base off of, but then it doesn't diversify the different kinds of questions we can do. But we begin with, again, a population. I'll put P for population, A for area, D for density as we need it. So population is 1.75 million. Let's write that out because it's possible that we need those numbers in a different way. There's 1.75 million people. And our area, it's once again a circular region. They have a 15-mile diameter. So let's get the radius off that as well. Give me one moment. Radius is 15 over 2, which is 7.5. And, you know, all this stuff is really important to look at as a whole and say, do I have the right numbers? Just because they gave me a number doesn't mean it's the number that we need. Sometimes, like the 1.75, it was in millions of people. 15 was miles, but it was diameter. What if they gave you instead the number of feet and you needed the number of inches, right? So there are conversions we're going to have to use time and time again. So the area here, pi r squared. I could have done this within the formula itself as well. I do not know 7.5 squared. I feel like I should. 56.25. Now this is, in terms of pi, this is square miles, and that is our area. So when we do density, we're going to do population divided by area. How many people in that given area? So 175,000, or per square mile, really, if you will, divided by 56.25 pi. Now, a little trickery when it comes to the calculator you may be using, at least ones that I sometimes, the ones that I use in my classroom for my students and the one that I'm going to use right here. The fair warning is make sure that when you divide by the 56.25 pi, you wrap parentheses around that, because these are multiplying together and your calculator knows order of operation. So the kinds of calculators you won't have to worry about this with are ones when you're writing it literally as a fraction, this over that, and then you know that the pi is in the denominator. But for mine, it'll be pretty important. Now I'm going to round to the nearest person, so I'll do 9903. So let's write the units out for that as well. So this density is about 9,900, but 9,903 people per square mile. All right, that's our number 1. A little bit of work, a little bit of talk, but we made it. Let's go to number 2. A circular region has a population of about 15,500 people and a population density of about 775 people per square kilometer. Find the radius of the region. Excuse me. Now, as I just said, to look into what you do need, don't need, and how to convert things, sometimes I check and see if they ask, it says find the radius of the region. It doesn't say in kilometers, in meters, in whatever. So I'm going to assume they want kilometers because they have square kilometers for area. So there's that. Now, on this one, we need the radius of the region. That's within area. So, we'll dive into that one as a whole. Density, once again, it's population over area, and this is a circular region. So this time I'm going to put the area of pi r squared right within there. We don't know the radius. We don't know the area. We do know the density this time, though. The density is 775 people per square kilometer. And we do know the population. So population being 15,500 people. So when it comes to formula, it is still set up the same way. Density equals population, 15,500, excuse me. That would have made a critical error. 15,500 out of our area, pi r squared. You can put area, but eventually I need r. And this might get me to work things a little bit better than not. My goal is to solve for r, in which case r is being squared right now. I need to get this out of the denominator. Do what you want with the pi. If I multiply both sides by pi, I'm going to have to bring it back down later anyway. So I'm going to leave it in the denominator. Let's do a two-step little dance here. Multiply both sides by r squared. So I have 775 r squared equals 15,500. Ooh, almost did it again. 15,500 over pi. So that pi didn't really move. And I know why some people kind of want to bring the pi up just to bring it back down, because they get confused when we divide here saying, where does it go? Well, this goes down with pi, just like the r squared was down there with pi. But there's my two-step to get r squared by itself. So I'm there. Let's see if 775 can divide out of 15,500 before I keep moving forward. It can. It turns into 20. So 15,500 divided by 775, y'all, is 20. That would become 20 over pi. Again, that pi hasn't moved. You might be, a lot of people, again, still have trouble with where does it go? Does it come up with it? Does it cancel out? Do I ignore it? Yeah, so there it is. And now I got to take the square root of both sides, right? 20 over pi isn't really anything to us. It's probably a little bit under 6. And we're going to take the square root to get this radius. And normally when they do something like this, it'll get somewhere close to a number. I'm guessing it'll be around 1.7. Excuse me. No, I guess it'll be, I don't have a guess. I'm guessing it'll be around 2.4 or something. Let's see. Divided by pi. And then the square root of that. Oh, it's a little more than 6. Oh no. Square root, then it's going to be around 2.5. Square root, second answer. 2.523. So I'm just going to go and round that. I'll say 2.52. 2.52 kilometers, though, right? We're talking about a certain unit of measurement, and that's going to be our unit of measurement for that one. So in terms of kilometers there. Hold on, I lost my page on something else here. Give me one sec. Okay, so that is number 2. Let's go to number 3. A furniture designer applies a thin glaze to the entire marble stool. How much of, it's right here. How much of that amount is needed for a stool whose linear dimensions are 7/8 times the dimensions of the given stool and 5/4 times the dimensions of the given stool? We could write those as percentages too if you ever wanted to. Like 7/8 I know that's 0.875, so 87.5% of something. 5/4 is 1.25, so 125% of something, or 25% increase. Okay, let's see what they're really asking us though. Applies the thin glaze to the entire marble, so how much of that amount is needed for a stool whose linear dimensions are that? So I don't know if we need the original in comparison to this, and the answers, by the way, are not 87.5% of it and 25% more of it because of area being a two-dimensional kind of thing. This is all about surface area. To apply the glaze to the outside, we need the outer surface to be covered. Let me think about how they're asking us to answer. How much of it is needed of the glaze? So I think we're going to figure out what the surface areas are in comparison with each other. And we will divide the final by the original. Okay, so whatever it is. Now, just so you're aware, the final answers will be, in case you're allowed to use this stuff, because I still don't know if the book kind of wants you to use this. We actually want to take whatever the original ratio is and square it. This is because this is two-dimensional. We're taking 7/8 of not just one dimension, but a second dimension as well. So you square both of those things. Now, I don't know, let's see, 49 over 64. I don't know that exact thing, but that would be the fraction of what it is. So 7/8 squared is 49 over 68 over 64, and whatever that number is as a decimal, 49 over 64. So I'm giving you the answer before giving you the extra work I'm going to do. So that is 0.765625. Either one of these will apply as far as this is the amount of times, right? Around 76, 77% of the glaze is needed for 7/8 times that amount. This one, 5/4 squared, or 1.25 squared. Let's see. 5/4 squared is 25/16. I feel like I should know that number. Is it? I don't want to spend time thinking about it. It's 1 point something. 1.5 something. Let's see. 25 over 16. 1.5625. 1.5625. So these will work for this one, right? You need about 56% more glaze in that other scenario. So those are the answers. Right? I'm giving them beforehand. Let's go to the math, though. Let's actually calculate surface areas of these things, and I will copy and paste this. Actually, I don't need to. I can draw that. I will draw out this original cylinder with the given height and diameter. Let's find its surface area. Then we'll apply 7/8 the amounts, 5/4 the amounts, and find their respective surface areas as well, just for surface area practice. Okay. Now, these are in terms of inches. So we got 16 inches going across here, which is good. 7/8 can work with that as a fraction. The 18, not so much. That will end up being a fraction. So 18 inches here for the original. Surface area of this guy, first of all, we do need radius for this. If this is 16 inches, the radius is going to be 8 inches. Now, surface area of a cylinder is 2 pi r, circumference times your height, plus 2 of those pi r squareds, the area of both bases. We have lateral area around the side, and then the top base and bottom base we're going to work out there. So we have a radius of 8, 2 pi times 8. The height is 18. And then 2 pi times 8 squared go in there. 16 times 18 would be 288. I think. So 288 pi plus, and that's 128 pi. And 288 pi plus 128 pi is 416. So 416 pi square inches. So let's calculate and round that thing, even though I'm not going to be using the rounded value. And honestly, I don't even really know if I actually need this number. I should probably just leave it like this. Actually, I will. I'm going to leave it just like this because I don't need the rounded number. I need to know how one's compared to these. So let's call this object 1. Object 1, object 1, object 1. So with object 1, we have that radius, that height. Now what we're going to do is take 7/8 of these values, and then we're also going to take 5/4 of these values and compute them, and then divide them from object 1 and see how they compare. So I'll consider this one here to be object 2 and this one to be object 3 when we take 7/8 and 5/4. I'm not going to redraw them. I'm just going to rewrite them. So surface area of object 2, if we take 7/8 of 8, we get 7. Right? 7/8 of 8 is 7. Not squared. Hold on. Not for this part anyway. Height. What is 7/8 of 18? 7/8 of 18. 18 is 9 over 4. 7 times 9 is 63. So we get 63 over 4. I guess I'll do this in fraction terms to begin with. And then we get that out. Eventually I'll get to that other number, but we should be good for now. 2/4 is 1/2. So we have that. And now that we just got to do 7 times 63, which is 441. So we get 441 pi over 2. And then 7 squared is 49 times 2 is 98. So that's 98 pi. 98 pi is also 196 pi over 2. Hold on. 196 pi over 2. And so ultimately, when you add those two together, you get 537, no, 637 pi over 2. Why is that different from the number I got here before? Oh, because we have to divide and compare these things. That's right. So 637 pi over 2 square inches. That's an exact number. You could divide it by 2. It'll have a 0.5 value. Probably not terrible. Let's get what that number is. That's 318.5 pi. I hope I'm doing all that right because I'm doing that in my head. So we got that number as well. What we're going to do now is compare surface area 2 to surface area 1. SA2 to SA1. And that's 7/8 dimensions that we had before. It's not going to be 7/8 anymore. It's going to be this other number here. Instead of 87.5%, it'll be this number, or as a fraction is 49/64. Now I trust everything I did right here was correct. It was calculated correctly. So I'm going to type in my calculator, and you'll see with me whether I did this right. If not, I'm going to eat a lot of crow on that and say just use the calculator. We got to divide one by the other. Let's jump to the calculator. I'm prone to making mistakes, especially mental ones, so let's see. Especially when I'm talking. When I'm talking, I'm less likely to know what I said. Now, I'm going to ignore the pi's because the pi's will just cancel out. So this divided by this, and we're getting, hopefully it's this number right here. Okay, good. And if you want to get the fraction conversion, the number that we saw before is 49/64. Okay, so I did everything right there. That's 0.76 or 5625. Actually, let me do the fraction first. 49/64, which is 0.765625. So either or will apply for that. Those are the answers that you just saw. This is the amount that we need in comparison to the original for glaze. The glaze is the surface on the outside, so it's a surface area thing that we compare. There's the first one. So you can do the first one like this as long as all dimensions are being doubled or tripled or 7/8 or 5/4 or whatever. And same thing with this one, you can square them for surface area. If we have a question like this for volume, I don't know if we do yet or not, I haven't looked at the problems, we'll be cubing these ones if everything is tripled, if everything is doubled. But if they're not, this is where we really got to put this practice into play. I still got one more to do, so this is going to be a little bit longer than I anticipated. Surface area of object 3, we do 5/4 of these values, and 5/4 of 16 is 20. Hold on, let me do this in the middle. 5/4 of 16 is 6/4. 16/4 is 4. 5 times 4 is 20. Now 5/4 of 18, not as clean. 18/4 is 9/2. 5 times 9 is 45. We get 45/2. If you want to write 22.5, you can, but I'm going to do mental math in here, and I'd rather use the fraction for that. All right, so 2 pi r h plus 2 pi r squared. Let's get it. 2/2. Gone. Did they cancel last time? Wait. Oh, they did. Oh, this was a 4 before. That's why. Okay, got it. I'm like, I don't remember something just outright going away. There was a fraction. Not this time. 20 times 45 is 900. We have 900 pi here. 20 squared is 400. 400 times 2 is 800, so 800 pi. All right. Easy numbers. Thank you. 1700 pi. So how does 1700 pi square inches compare to the original? We're going to get 1700 pi over 416 pi, which again, the pi's cancel out here. I should probably even just show that. Those parts are gone. That's why just in terms of pi is better, plus we're not rounding early. Now this number should be the same as the 1.5625 that we got before through that other division. So what's 1700 divided by 416? Oh, no, that's not going to be... I want to mess something up. That's not going to be 1.5625. What did I do wrong here? That's 4. Uh-oh. Okay, let me see what I just did here. 2 pi r h plus 2 pi r squared. 400 times 2 is 800 pi. Let me see what the heck I just did here. Give me 1 second. Okay, it was a quick catch, but I still got to fix some things. I'm not supposed to use 16, right? I'm supposed to use 8 here. So 8 is my radius, and I used 16. So my bad on that. So 8. 5/4 of 8 is 10. So 10 goes here. 10 goes here. Sorry about that. And 10 goes there. So let's fix some of these numbers. Hopefully, I think they'll still be clean. Okay, whoopsie. I hate making mistakes for you guys here. It's one of those little things that really should not be happening. 10 times 45 is 450, and then 10 squared is 100 times 2 is 200. Oh, 200 here, 450 was 200 is 650. Okay, that should be better. 650 pi. So let's do 650 pi over 416 and pi, and let's try that one more time. That number at least looks like it can properly divide it. There we go, 1.5625, which was also 25 over 16. So 25 over 16, which is 1.5625. Let's take a look at the fraction equivalent. 25 over 16. Okay, so we've completed that one as well. That's how many times bigger that's going to be. And like I said, you might have to go that full amount of those parts of the problem. Let's call that part A and part B. So part A begins there. Part B begins there. That's a lot for that part of the problem. 21 minutes in. One little mistake. We corrected it. All good. Okay, that is section 1.1 on modeling with area, population density. Section 1.2, modeling with volume, we deal in density as a whole. No example right here, no problems on this side. Let's look at the example. The diagram shows the dimensions of a bar of platinum. Credit Suisse. I have a lot to say about them these days. Platinum has a density of 21.4 grams per cubic centimeter. Find the mass of the bar to the nearest gram. Okay, so this one deals in density as well, and they have the examples written out. Now, they do say to the nearest gram, and they say per cubic centimeter here, but the things they list here are millimeters. So the very first thing you'll probably want to do is convert these values to centimeters. Every 10 millimeters is 1 centimeter, so we divide these by 10 to get the centimeter values, and they're doing that right here. It's basically a decimal shift of 1 decimal to the left, and then they're going to calculate the volume. Now, this has a rectangular prism appearance. There's a little bit of curvature, but we're rounding. So length times width times height, area base times height for this rectangular prism is this number here. That's in cubic centimeters. So when it comes to density, we have cubic centimeters taken care of. We need to find the mass. The mass will be in grams. Density is mass over volume. This is the classic density version, not just population density of this over that. But this one's mass over volume, and we need to find that mass. They're calling it X. Here's the density that they gave us, 21.4 grams per cubic centimeter. Multiply both sides by the 4.8-ish number. You get around 103 grams of mass. So that's a really good example as far as what they're covering on that, the kinds of things you're going to have to do. We'll see if that's the same kinds of questions you do have. Let's see. Let's start it off. Numbers 4 through 8, starting with number 4. Bar of platinum, same thing. So they are starting off pretty standard. Pretty similar. A bar of platinum has a mass of about 100 grams. This time we have mass, 1,000 grams, excuse me. It has a width of 51 millimeters and a height of 9.7 millimeters. Find the length of the bar to the nearest millimeter. Now, we're going to have to use, I think it was 21.4. Let's use their density that we had because they told you what the density is. That's constant for all bars of platinum. It doesn't change, just like density of water or something. So 21.4 grams per cubic centimeter. We're going to use that. Density is 21.4 grams per cubic centimeter. There's a problem in the actual textbook where they gave you something. They didn't provide what the density of the thing, or not the density, the conversion factor for gallons to cubic inches or something like that. And it was, or cubic feet, I think. And that was something we actually had to look up, which was really crazy. This time they did. It was just on the other page. So density is mass over volume, right? M over V. So we have that. Let's replace density of 21.4. Notice they are, so it's cubic centimeters. We have cubic centimeters in this density. Leave that. Don't just multiply that by 10. You'd actually have to multiply it, I think, by 1,000 to change it. So if you don't know that, that's okay. We're going to deal in terms of centimeters to start. We'll convert to millimeters at the end. So density is mass over volume. Now, our volume, we have a width of 51 millimeters, which is 5.1 centimeters. We're going to use that number. We have a height of 9.7 millimeters, which is 0.97 centimeters. Now, we don't know length, when we get the answer for L, because we're using centimeters now, it'll be in centimeters. And then we got to multiply by 10 to get the millimeters after. So we're going to do 5.1 times 0.97 times L. That's our volume. Length times width times height. Okay. So my case for this one, if you saw one of the previous problems, I can kind of switch places here. I can multiply both sides by L, get that by itself. Once I divide both sides by 21.4, and now the 21.4 just basically goes down here. So the L's are gone on this side. Boom, 21.4s are gone on this side. And now I'm going to use the calculator to compute 1,000 over these three numbers multiplied, right? So let's go to the calculator. Let's check that one out. Be very careful again on order of operations. So I'll do 1,000 divided by, one of these parentheses here, 5.1 times 0.97, and I would practice this. Don't just rely on what I have here, times 21.4. You might make a mistake otherwise without the parentheses the way they are. So here we're going to get 9.4459, 9.4459 about. This is in centimeters, and we need a millimeters answer. So when I multiply this thing by 10, then I'll get the length of that thing. So it's around 94, I'll say 0.5 millimeters. So all told, that's what we're working out for that one. That's the answer that we're getting. Looking pretty good. Did they say to the nearest millimeter? I'd say 95. Oh, wait, what was it? 94 point, where's my calculator? 94.45. So, oh, it's right there. So 94, around 94 millimeters then. Still trying to answer the question being asked. They said nearest millimeter. We got it. Okay, let's jump to number 5. Let's see, 5, 6, and 7. Describe how the change affects the volume of the platinum bar in the example. So we're still back to the same platinum bar. Doubling the height. Oh, affecting volume, by the way. Affecting volume. So volume, length times width times height. What if we just double the height? How does the volume change? Did they give us volume? They gave us volume in terms of cubic centimeters. If you're fine, we can work off that. We can do the, let's just use that one. So let me write that. Volume is 4.81593 cubic centimeters. I believe that would also mean that it's 4815.93 cubic millimeters. It would be 1,000 times more. So you can use one or the other, whichever one tickles your fancy most. Let's make sure that actually would work. 49 times 28 would be something in the hundreds and thousands. Yeah, I think that would be it. So you can use an either or case. It doesn't matter. You want to use millimeters? We already converted it. All right, we already converted it. So here's the original. Let's do doubling the height. The height goes from, this is the problem, we have to go back and forth, 3.4 millimeters to double that, 6.8 millimeters. Now, spoiler alert, your answer is going to be double what this is. So about 9631.86. 9631.86. I think I'll get that right there. So volume of object 2 is going to be, I need all the numbers. I need to stay on this page. We already know we're doubling the height. So length times width times the new height. Like that. So let's go to the calculator. We'll do 49.7 times 28. 9631.86. So that is the answer I wrote before that. So 9631.86 cubic millimeters. You might say, well, Mr. Robinson, why don't you square it? And I said, well, squaring only had to do with surface area or area things. Like, oh yeah, that's right. Yeah, why don't you cube it? Because we didn't cube, we didn't double every dimension. We just did one dimension doubled. And that's what was the question? How the change affects the volume, because that is the volume answer. So let's compare one to the other. Oh, it's double. That's right. So V2 over V1, it's 2 times more. 2 times double the overall volume. Okay, that's number 5. Now, numbers 6 and 7, we still apply these things. It's the same original volume. Let me write out what we're actually doing with them. So this is double the length. Now let's double length, or double the height. This is double the length and width coming next. So double length. The length is the longer of the two, 49.7. Doubled is 99.4. Double the width. We're doubling 28.5. That's 57. We're keeping the height the same. We're not doubling the height anymore. So doubling two things would lead to 4 times as much as what you had before. This number should be close to, I don't think I'm going to get it exact this time, 192. 19,000, I'll try it, 19,263.72. 19,263.72. Did I say that the same way I just wrote it? We'll see. Okay, so we're going to do volume as double the length times double the width times double the height. And the original height was our 3.4. Because we're doubling two things, so it's 4 times as much. And that's what I was trying to do in my head there. So let's go to calculator. 99.4 times 57 times 3.4. 19263.72. Yep. 19,263.72 cubic millimeters. Now, that's the volume, the question they're asking once again. And again, I don't know if you're allowed to do what I'm doing here. This is that number times 4, the original volume. So that's where we're getting, I'll call this V3. V3 over V1 is 4 times as much, quadruple. Because we're doubling not every dimension, so, we're doubling 2 of them. There we have it. Number 7, multiply the length by 1/3. We're taking a single dimension 1/3 times. That means we're dividing our original volume by 3. The original volume was this 4815, and we're dividing that by 3. I'm no good at that. Oh, maybe I am. 1605.31. 1605.31, I believe, is going to be that one. Okay, I'm feeling mentally okay with some of my math right now. So 1/3 of the length, the original length, having been 49.7. That's the part I don't know how to divide by 3. Because it doesn't divide cleanly by 3. Right? I'll just probably write it as 49.7 over 3. Let me check. 0.7 over 3. Yeah, it's not clean, so it's 16.56 repeating. I'll just write it as 49.7 over 3. Hold on, my phone is over here. Let me get rid of it. Okay, so that's the millimeters of this guy. And again, we're going to take 1/3 of what we have. There's a 3 that must be able to cancel here. Yeah, somewhere. There's something that must be able to cancel. So our volume of object 4 is our new length. I'll let the calculator take care of it anyway. Times the width. What's the original width? This is the hard part. I have to go back. 28.5 times 3.4. 28.5 times 3.4. I'll just let the calculator take care of that one. But you can notice, I mean, look, what's the difference between this and the original volume? Just somewhere something gets divided by 3, and that's it. Just something once somewhere gets divided by 3. That's how it compares. That's why it compares. So we do divide that thing by 3 ultimately. 49.7 over 3 times 28.5 times 3.4. And yeah, something worked out. 1605.31 cubic millimeters. I'm not really a fan of these questions because more so, I'm sure I'm practicing volume calculations, yeah, but I don't know to what level we're expected to be writing these things to our knowledge of like, yeah, we just divided by 3, or we do the volume thing again. And it's 3 of the same question. It's not even a density question anymore. So 4 over 1, when you do that, look, you eventually get 1/3. It's 1/3 times the amount. Divide this by the original that, and you'll get 1/3 of it. That's exactly how I got the number to begin with. 1/3 times 1/3 And none of these questions ever were for surface area for doing they were in the last set, but they never were for individual dimensions, and the volume ones never had all three dimensions affecting one thing. So I still don't know where they're getting at with those questions as a whole, but that's okay. All right, number 8. Not questioning the book. No, not at all. Not at all. Anyway, Credit Suisse. Part for a toy train is made by drilling a hole that has a diameter of 0.6 centimeters through a wooden ball that has a diameter of 4 centimeters. So this hole, I guess it's a cylindrical hole. So inside here, and I guess it comes out the other side. Inside here, you basically have a hollowed out thing like that, I guess, is the way that I'm seeing what they're talking about. Let me actually, let me copy and paste this thing over. I can enlarge it and draw it better on this other side here. So, there we go. Better off that I use what they're talking about there. I'll read the thing again. A part for a toy train, oh yeah, I can probably thread, is made by drilling a hole that has a diameter of this through a wooden ball. There's a diameter of that. Estimate the wooden ball. If the hole is made, do the surface and volume of the wooden ball decrease after the hole. Ooh, okay. We don't have to calculate part B, which I guess is nice. Okay, so let me do this one more time. So there's going to be a hole coming out of, the bottom there, like that, and this is cylindrical in nature. Now, they mention diameters of these things. This has a diameter of 0.6 centimeters, which means the radius is 0.3. I care much more about the, I don't know if you can see that, but I care much more about the radius in this case when it comes to this object. I'm going to call this one object 2, the littler guy, that guy, and this will be object 1 over there. Maybe you can see that better. This one has a diameter of 4 centimeters, the sphere, if you will. That's 4 centimeters. Now, sorry, so the radius is 2. Now, I do need the diameter, though, still for one thing. So this may be 2 centimeters. I still need object 2's height. Remember, when we cut this hole into this cylinder, and this won't be perfect, they said estimate. Keep in mind, if I cut a hole through a ball, and strangely enough, I don't have a ball right here. If I cut a hole through a ball and it has some thickness, some of the curvature top got lost. So this height of the cylinder won't be exactly the same as the diameter of the ball. From top to bottom, it's going to have lost a little bit there. It's not going to be exactly 4 centimeters, but they said estimate it, and that's probably where the estimation comes into play, where a little bit is lost. If this is indeed a cylinder, this height of object 2 will be 4 centimeters. At least in comparison to what we have there. So we have 2 objects. To find the volume of the wooden ball after the hole is made. It says explain your reasoning. I feel like my math is going to be my explanation. I'm going to find volume of object 1 and subtract volume of object 2. V1 minus V2. That's my explanation. Drill the hole, work that out. I have a diameter that will represent the height of the cylinder. I have a radius of this ball. Let's find the volume of object 1 given a radius of 2 centimeters. Remember, it was a diameter of 4. Volume of a sphere is 4/3 pi r cubed. So we're going to work off that. 2 cubed is 8 times 4 is 32. We got 32/3 pi cubic centimeters. That's object 1. That's not the answer. Volume of object 2, we're going to do area of base, pi. This is our radius for this guy, 0.3. Pi r squared times that height, that 4. And it's a little less than 4. I don't know how much less. I'm not really using calculus or whatever I would need to figure it out. Maybe you don't need calculus, but not actually figuring out the exact number there. That's why they said estimate. 0.09 times 4, I believe, is 0.36. So 0.36 pi square centimeters. I'm going to double check that. Of course, I don't trust my own math on that one. 0.3 squared times 4. It would help if I use the exaction. Yeah, 0.36. So 0.36 pi versus the 32/3 pi. That's about 10 pi here. So significantly larger volume of this sphere compared to the cylinder. It's why I almost don't trust, cubic centimeters. It's almost why I don't trust what I just wrote there, but I'm going to have to go with it. So volume of the total. Now, one of them's a fraction, one of them's a decimal. It doesn't matter. I'm going to use pi in the end and with my calculator. 32/3 pi If you want, I can write this as 36/100ths, 18/50ths, 9/25ths equals 9/25ths pi. Like that, 9/25ths pi. It doesn't matter. It's exact no matter what you do. So let's do this one. I'll do 32. Oh, this did not work. 32 pi over 3 minus 9 pi over 25. I'm getting around 32.379, so 32.38 cubic centimeters for that volume. And again, I'm probably not going to type out an explanation, but being a composite solid, what we're doing there is we're subtracting the volume of the cylinder from the volume of the sphere. And remember, that cylinder's height is about equivalent to the sphere's diameter. Not exact, because when you cut out the hole, the cylinder probably doesn't meet at the very tippy top and the very bitomy bottom. And that'll be our part A. Now, part B, they didn't ask us to compute anything, which, you know, even if we did, it would also be an estimation in and of itself. And it would take a little bit of time, not in full. But they say, do the surface area and volume of the wooden ball decrease after the hole is made? Explain. Well, clearly the volume did, because we subtracted something from something else. So as far as volume goes, there's less of the ball in the end. There's less of the sphere. Oh, we might have to do a computation. I take it back. I think we do have to do a computation for surface area. For volume, so it's going to take a while, but I'll explain what I think it is and why I think it is. But for volume, the volume decreases. So it decreases because you are losing volume of the ball. You are subtracting the whole, the cylindrical portion from the overall volume, making it lessening it. I don't know. Surface area is a little bit trickier as far as it's not always, well, for sphere cases, maybe not. It's not always what this answer is going to be here, but here's my prediction, and we are going to compute it. If this is all you want to write, then go ahead. But there's a chance in some situations where this wouldn't be the case. For surface area, here's the thing. I don't think it's less than. I think it increases. Now, here's why. Remember what surface area is. Surface area is the amount of surface that there is, not just outer surface as far as outside of the thing. Outside also includes inside that cylindrical portion. This cylindrical wall, if you will, this thing that I'm going to kind of paint red right here, the cylindrical wall that's inside of that thing, it may be a hollow volume, but that is wall. That is stuff that if you had to paint this thing, if you had to coat it with that thin glaze and whatever, you'd have to get that inside portion. That's actually adding surface area to your overall thing, which would make it more. You are losing that top and that bottom, though, which are, for the most part, not perfect, for the most part, pretty much just a circle on top and a circle on bottom. So the question becomes, is the circular area of this top in green, or in blue, and this bottom in blue, is the circular area of these two that are removed greater than or less than the lateral area of the cylindrical wall that's there? Or are they equal? I doubt it'll ever actually be equal. And I'm guessing for this one with such a small radius and such a large height, I'm guessing it's going to be an increase. I mean, by saying guessing, I mean it's going to. But let's actually compute it. Now, if you want to move forward beyond this one and no computation, that's fine. But the cylindrical wall is added surface area to the overall sphere, despite the fact that the top and bottom, and I call them circles in quotation marks because they're not exactly flat two-dimensional circles. There's a little bit of sphere involved, surface area-wise. It's going to be really a non-factor when it comes to comparing the two. The top and bottom circles are removed from the overall surface area because their areas together are not as much as that lateral area that is added. And I recognize the book never uses the phrase lateral area. I'm talking about the cylindrical wall portion of that. So here's what we're going to do. I'm going to compute this part. Feel free to move on to the next question if you'd like to. This is more of an in-depth exploration on this thing. We already did the volume, right? We computed this one, and the original volume would have been 32 thirds pi, which is... What? 32 thirds pi is... it's more than the other number, but it's not much more. Let's see. It's going to be in the 30s still. The original volume, 32 thirds pi, is 33.5. We only lost 1.12 cubic centimeters of volume. There wasn't much lost here. I don't know if this ball is a drawn to scale thing. Actually, it's clearly not. But yeah, that hole is significantly smaller than you think it is. But yeah, I think surface area is going to be added here. So here's what we're going to do for surface area, if you want to stick around. I got object 1, that is the sphere. That's 4 pi r squared. Wait a second. Oh, r is not 0.2. I was going to say, wait a second, I squared 0.3 last time. R is for this guy. Okay, 4 pi r squared. 4 times 4 is 16. So 16 pi square centimeters of original surface area volume. Now, the next object, I don't want to find the surface area of. I want to separately find its lateral area and its base areas. The lateral area is a cylindrical wall. This will be added to the overall surface area. Now, lateral area is circumference times height. So 2 pi r times height. Was that 4? 2 pi r times height. Boom. So that's 8 times 0.3, which is 2.4, I believe. Even if I'm wrong, it's not. It's going to be the answer that I want. The question, and listen, we don't need overall surface area. We just need to know if the lateral area minus the 2 base areas is a positive number or a negative number. Really, that's the only ultimate question, and I think the answer is going to be a positive number. Base area is pi r squared, and pi r squared is 0.09 pi, so 2 bases is 0.18 pi square centimeters, significantly less than this other guy that you have right here. So when we find the surface area of the total thing, surface area of total, we're going to be doing the surface area of object 1. Oh, this is object 2, by the way. Surface area of object 1 plus lateral area of object 2 minus the 2 base areas of object 2, which will be a net larger value. It'll be net positive. Large value, it'll be an increase. So 16 pi plus 2.4 pi, and I think I got that number right. I'm just going to trust it. Minus 0.18 pi, which is 16 plus 2.4 minus 0.18, 18.22 pi, which is more than 16 pi, right? Pi square centimeters, and then times pi. 57.24 square centimeters. So that's more than the original surface area of 16 pi, which is probably around 50. I think we've seen that number before, 50.27. So 57.24 being more. So yes, we are adding some in comparison to what we had before, and I think I'm good. I think I'm good on the whole thing. Very long problem as a whole in general. Yeah, this review is significantly longer than I expected it to be. We're only 8 problems in out of 18, and about 15 minutes in here. So yeah, hopefully we're getting all learned meanwhile. Okay, we're going to move on to section 1.3. Now, section 1.3 is on cross-sections of solids. This is one where I still struggle drawing-wise, making everything to your standards and what you'd like to see on that. Just hold tight and see what it looks like. Definitely use their drawings more so, because I have to draw my own. Definitely use their drawings as the best representation of what cross-sections are. When a plane, the thing, the orangey, salmony color, intersects with this solid, you get that purple cross-section, that two-dimensional representation of when it slices through, what does that facing look like? In this case, this hexagonal pyramid, when cut through the middle vertically, down an edge, both those edges there, the middle of the edges and the apex, you get a triangle, probably an isosceles triangle, if that's a regular hexagon. So describe the shape formed by the intersection of the plane and solid. The cross-section is a triangle. It's this one here. And remember, it's 3D represented, so it's likely that these two angles are congruent to each other. Maybe they're both. I don't know, 70 degrees or something like that. But that's what we're seeing with that one. So we're going to do the same thing with numbers 9, 10, and 11. These should be the quickest of the questions we've had so far. Describe the shape formed by the intersection of the plane and the solid. I'm going to leave the thing as it is and as it looks. You have a pentagonal prism that's knocked over, and then something going flat through the bases. Remember, those are pentagon bases. And you're creating a rectangle, right? You're creating a rectangle right there. Those are both the same lengths, and they make right angles, and diagonals are congruent. The cross-section of this one is a rectangle. I'm not going to do much more to these because they're already drawn. So I just get to move forward. Awesome. Number 10, you have, based on the appearance of the 4 congruent sides, a rhombus, but based on the right angle, it's a square. So a square base, and this plane is parallel to the base as it crosses through the square pyramid. It is a square in and of itself, similar to it, as all squares are similar, but not congruent. It is a square, a smaller square than that of the base. And number 11, you can see a triangular, the same thing. A triangular prism, not the same thing. Triangular prism, but parallel to the bases, is going to make a triangle here as well that is congruent to those other triangles. No saying on whether the triangles isosceles are equilateral. It is just a triangle cross-section. Thank you for the drawings. I very much appreciate it. That was number 11. Okay, we're going to deal with number 12 and 13, where they ask, for us to draw the cross-section formed by the described plane that intersects the red line segment drawn on the solid, what is the shape of the cross-section? So when your plane is parallel to the base, and they get it started for you a little bit, they draw one of the lines, and I think that's where I learned to do this best for you guys, was I don't actually draw the plane itself, I just draw the kind of the cross-section. But this would be cutting through parallel to these bases, which means it's going to make the same shape out as these ones, just like number 11. So here they intersect through that. You're looking at this red cross-section here. You make a pentagon much like the pentagons you see on top and bottom. They're in fact congruent to that one. So there's the drawing. There is the cross-sectional shape. Number 13, let's copy and paste that one, parallel to the bottom face. Now this is a trapezoidal prism. The trapezoids on the front and back are technically the bases. That's why they're not calling that bottom thing a base. So this will not necessarily make a trapezoid out. It would if it was cut vertically, but because we're parallel to that base, we're probably going to make something similar to what the base looks, the bottom face looks like. So it's going to be coming here and across here and across here. You might say this looks like a parallelogram or rhombus, but keep in mind this is a three-dimensional representation. That's a rectangle, right? This is rectangular, just like that bottom part is, that top part is too. This is a rectangle of that guy. So they're giving us kind of easy questions with compared to that we had to do in the past. I don't know. I felt pretty good on those ones, and at least this is a fast section in comparison. Because we'll have 5 more problems now, but after this section, just 4 more. Probably on the last section. Number 14, describe and draw 2 cross sections that can be formed by a plane intersecting the solid in exercise 12. Okay, that was this one. Let me copy that. Give me a second. They said two cross sections that can, let's do 2 separately. We're gonna have to kind of ignore what's already there with that red line. 2 cross sections to be formed by intersecting. The shapes of the cross section should be different than the shape of the cross section in exercise 12. Okay, so let's do one that's like vertical through it instead. So totally ignore that red line if you can as much as possible. I'll make a purple line. Let's do one that goes down right here. Okay, so it's going vertically down into it, basically like that. So it's going to go across like that after, and then boom, and up through there, and that's where we'll get a rectangle. Did they say describe it? Describe and draw. So there's the drawing, so my description, that is a rectangle. So I'm slicing it that way. They said do another one. I want to make sure it's unique from the rectangle. Let's do one that goes like diagonally in and out. Do I go crazy with it? Let's go across these corners here. Actually, let's go across the back. Let's go across the back corners here, and then these 2 front corners. This will be very skewed, and I cannot guarantee, oh, I could. It's probably a regular pentagon. So I can probably guarantee parallel. Well, it is parallel. This is a prism. So it's going in and out this way, but take a look. These two are absolutely narrower and closer to each other than these two are, right? If this is congruent, then these guys are congruent here, right? But not from this to this. That diagonal is going to be longer. So these will be parallel to each other that way in that cross section. I actually like that appearance of it. It's like a ramp going in and through it. And it meets at the corners there, so that'll be a trapezoid. So that's kind of an interesting one that I made. But it works out. It goes in and out like that, and I wanted to make something unique and different from the Pentagon. So I never truly drew planes that cut through. They did, and hopefully these visuals are good enough for you to understand what those ones are. All right, I have one more section to go on solids of revolution. So that was a very fast section in comparison, which is cool. Let's go to solids of revolution. They have a couple of examples. A part A, which is completely independent from part B. Let's take a look. Sketch the solid produced by rotating the figure around the given axis, then identify and describe the solid. So here's the original. They take this and they say, all right, we need to rotate this around this axis. When you do, you make this cylinder, right? You do this like going around there and going around there and connecting those dots. There you get that cylinder appearance just like they have. Radius is 3, height is 8. Remember, height is distance between your bases. These two circles are the bases of it. So the solid is a cylinder with a height of 8 units and a base radius of 3 units. That's part A, completely different part from this B. These are just two different, totally separate examples. So there's A. B, sketch and describe the solid that is produced when the region enclosed by y equals 0, x equals 0, and y equals negative x plus 4 is rotated around the y-axis. So first of all, the region that bounds that is this one triangle here. They do this reflection piece, not a requirement, just something that you can do to draw the rotation, and we do revolve around y-axis. So they reflect across the y-axis to then create their revolution, which is, it's nice to do. I kind of see why they do that. But yeah, you would rotate it around here. Because this is on a graph, you can keep the distances the same like that. If we have to do graphs, I will attach graph paper. But there is that cone that they make. Now this cone has a radius of 4. It has a height of 4. They said find the volume, but we do need radius and height for that. So volume of a cone is 1/3 area of base times height, pi r squared times h. You get 64/3 pi, which is about 67.02 cubic units. Yeah, whenever they do these ones, they tend to not have like inches and things like that. It just tends to be just cubic units, square units, things like that. All right, let's go to numbers 15 through 17 all together now, where I can copy and paste these. You might have to draw them. Sketch and describe the solid produced by rotating the figure around the given axis, then find, surface area and volume. So we're going to have a few things to do on these questions. Let's start with number 15. And it looks like number 18 is something to graph, so I will be attaching graph paper for you. So on number 15, this thing rotates around this axis here, so whatever was 5 there becomes 5 on that side, right? That's why they tend to draw that thing first. And then it goes around. So we make a cone. Okay, and if you want to learn more on this, obviously I did the 1.4 section, so you can take a look at that as well. But it makes a cone. The radius is 5 units. I'll just put 5, and the height is 9 units, like so. Now we do need to find the surface area and volume of this thing as well. I tend to start with volume. I think it's kind of I think you learn volume first of these before surface area. So volume is 1/3 area of base, pi r squared, times height. 1/3 of 9 is 3. 3 times 25 is 75, so you get 75 pi cubic units. They don't say leave in terms of pi, so I'll be doing 75 times pi. 75 pi. It's about 235.62. 235.62 cubic units. That or the other, I'll take it. Surface area, on the other hand, we have to add the lateral area, the party hat. That's pi times radius times slant height. We still have to find that. Plus the area of the base, pi r squared. We know the area of the base is 25 pi. We already got that one. Slant height is this L. We need to find this guy here using Pythagorean theorem with the 5 and the 9. So 5 squared plus 9 squared is L squared. And that gets 106. So L is the square root of 106. It's not a prime number, but it doesn't. 2 and 53. I think 53 is prime, so I think root 106 is the best I'm going to get there. So surface area here will get pi times radius times slant height, like that. So as an exact number here, we'll get 5 pi root 106 plus 25 pi, and I'm not factoring out a 5 pi from there. So that's square units, and let's use the calculator for that, guys. So 5 pi root 106, and then plus 25 pi. All right, 240.26 square units. Okay, that was just one problem on number 15. Hopefully that's kind of connecting. I'll leave that there for you to absorb what we had to do, because we had to do a few things there, right? First of all, we had to begin with identifying this, and once we identified it, we could do the volume and surface area properly, right? They have different formulas based off it. So the revolution there and the radius and height, as much as we described what these things were, and they're a part of the answer too, we used these parts in our calculations. All right, let's go to number 16. Let me make sure I'm still on the screen with you. Okay, number 16. I imagine we'll get done by the hour 15 mark. We rotate around this. We're going to make a sphere from this one, y'all. Oh, let me give you the whole beige thing. I don't want any white space there. There we go. I don't want it to look awkward when part of that space is cut out. So this 7, it rotates around 7 units this way as well, right? You make a sphere. Spheres aren't my area of expertise when it comes to drawing them. Clearly. I think you can tell that that's a sphere, right? So it's a sphere. There's only one property of a sphere that we're interested in. That's radius. And the radius is 7 units. Now volume of a sphere, we just saw this before. That's 4/3 pi r cubed. 7 cubed is 343. I don't know what 343 times 4 is. I could do it, but I don't want to be wrong. 343 times 4 is going to be... No, not 343. 243. Hold on. 7 cubed. Don't be wrong. 343. Okay. 343 times 4 is 1372. So we got volume as 1372 pi over 3, or thirds pi. That's cubic units. Let's go ahead and do that full calculation. It's going to be a little more. It's going to be right around 1400 divided by 3. 1436.76. It was actually closer to 1372 than it was to, or excuse me. It was farther than, 1372 was closer to the answer than 1436 was. Okay, oh, not pi. What did I just say? This is cubic units here. Okay. Surface area. Surface area is 4 pi r squared. So 4 pi times 7 squared. 7 squared being 49. 49 times 4 is 196. So we get 196 pi square units. And 196 times pi. A little faster than the last question, I think. 615.75 square units. Okay. Let's jump to number 17. Now 17 has 2 different shapes in one, where it's going to take a little bit of work. We're going to have to work it. We're going to have to add possibly some things when it comes to volume, right? It's more of a composite solid. So I have no name for this thing. It's like a sideways facing parachute or sideways facing buoy, jagged edged buoy. We got to go 8 units this way. We're definitely seeing radius with that. So 8 units here, 8 units there. It's a semicircle on that part. But remember, this is 3-dimensional ultimately in the end. This thing's got to rotate. I don't know if my rotation appearance is going to be best for y'all, but it's 3-dimensional, right? So it's rotating along there. I have no name for this thing, but take a look at it in 2 phases. There is the hemisphere, and there's the cone. There's that full cone. So there's an object 1 and an object 2. I'm just going to name them based off that. So there's a cone and hemisphere. Now for both the cone and hemisphere, the radius is 8 units. The cone has a height though. The cone has a height, and the height of that object 1 is 6 units. So the volume, let's do volume first. The volume of the total is going to be V1 plus V2. So let's find volume of object 1. That's 1/3 area of base, pi r squared, times height. 6/3 is 2. 8 squared is 64, times 2 is 128. We get 128 pi. Let's leave it like that for now. It's cubic units. We'll be adding it with the hemisphere. Now, we just heard before the volume of a sphere is 4/3 pi r cubed. Well, this is a hemisphere. It's going to be half of that. So that's going to be 2/3 pi r cubed. So 2/3 pi times 8 cubed. Same radius, right? Same radius as the cone. 8 cubed is 512. 512 times 2 is 1,024. So we get 1,024 thirds pi, which shouldn't be able to reduce because 8 cubed and 2, no, they can't reduce. So let's do that. Let me make sure 8 cubed times 2. Awesome, 1,024. Okay, let's do 1,024 divided by 3 times pi plus 128 times pi, because that'll be the ultimate addition of what we do. I won't write the exact. We'll just go volume total. So volume total equals 128 pi plus 1,024 thirds pi, which is about 1474.45 cubic units for volume of those two. Okay. All right, let's get to the surface area. Surface area, this is where we have to go. That circle, remember this is a circle right here, right? That part, that circle is the cone's bottom and the hemisphere's bottom, or whatever you call it. It's covered. It's not a part of our surface stuff. There are only two surfaces that we care about. The lateral area of the cone, the pi RL, so the lateral area of object 1, plus, I guess you can call it the lateral area of object 2, the hemisphere, the lateral area of the hemisphere. So the cone will be pi RL, and this guy will be, remember 4 pi r squared is the surface area of an entire sphere, so hemisphere will be 2 pi r squared. But we don't add an additional pi r squared for that bottom circle. This is all we're going to do, just these two things here. Let's start with the 2 pi r squared because we have radius, that's 8. That's 128 pi. This is square units, by the way, when we do all this. So that's 128 pi. Pi RL, we never got the lateral area yet. This is 6, this is 8. 6 squared plus 8 squared, guys, that is 10 squared. This will be a 10. You can do L squared equals 36 plus 64. L squared equals 100. L equals 10. So the slant height, that L is going to be 10. So we do pi R, pi, sorry if I went fast on that. My 3, 4, 5 triangles is something that you want to really be attuned to these days. Pi times 8 times 10, that's 80 pi. So 80 pi plus 128 pi gives us 208 pi square units. 208 pi, 208, 635.45 square units. So there's our surface area of number 17. There's our volume of number 17. And I didn't really know how to name the shape, but it was a cone plus a hemisphere together. Okay, last question of the review, number 18. Sketch and describe the solid that is produced when the region enclosed by y equals 0, y equals x, and x equals 2 is rotated around the y-axis. Then find the volume of the solid. I think I'll need more room than just this on binder paper sense, and I will copy this graph paper stuff for you guys for the one problem you'll need. So let's go to it. Number 18, here's our system. We have y equals 0, which looks like that. Probably want arrows, but I'm going to get rid of these anyway. Y equals x. Y equals x has a slope of 1 and y-intercept of 0. We're looking at this thing right here, for example. I'll draw it as in full as possible. Boom. And then x equals 2. So x equals 2 is this vertical line, like that. So the region that we're talking about that's bound by these three, where's my purple? Right here, is this guy right in there. So I'm going to get rid of the lines in a moment once we understand the bound region, and then I'll redraw this as just a single triangle. You can probably enclose that as a whole, but getting rid of those three. Okay, so we're talking about just this guy right here. Okay. Now we're going to revolve this around, I think they said the y-axis, which will make a weirder looking shape. Rotate around the y-axis. So this is going to be, and if you've done the sections with me, you've seen this before. See, if we did around the x-axis here, then we'd be making a cone. Okay? But we're doing it around the y-axis right here. So around the y-axis means we're not making a cone. We're making a cone that's taken out from a cylinder. This is one of the ones that's harder to imagine and picture, but we have this 2 distance that's going to go on the other side, okay? This is also going to go on the other side 2 units, but there's a hollow inside-ish. The cone portion is hollowed out. Actually, this drawing's going to look kind of cool. So we got that, okay, but there's that inside right here that's not there, if that makes sense. There's a cylinder, and we cut out this cone inside of it. So hopefully that's making sense what we have. We got to find its volume. So we have a cylinder, and we got to take away the cone. So object 1, object 2. Cylinder is object 1, cone is object 2. Now, the cylinder and the cone both share the same rate. Well, actually, this isn't going to be too hard because they share the same radius, they share the same height. So cylinder minus a cone, they both share a radius of 2. They both share a height of 2. This height goes up, down 2 units. This radius goes across 2 units like that, right? 2 and 2. So radius is 2, height is 2. And the formula for volume of a cylinder is area base times height. So pi r squared times height. Volume of a cone is 1/3 area of base times height. So honestly, what we're doing is we subtract one from the other. We end up with 2/3 the amount, right? Volume of the total. This minus that will be 2/3 area base times height. Listen, you can compute any way you want. I'm just kind of recognizing patterns from these things. All you're left with, when you take away 1/3 of a whole amount of something, you're left with 2/3 of that amount. I got rid of pi. 2 squared is 4, times 2 is 8, times 2 is 16. We get 16/3 pi. This is cubic units, and it'll probably be somewhere around a little more than 16. 16/3 pi is 16.76. 16.76 cubic units. So it depends on how you want to actually work out what we actually did there, for finding the volume. I did it in the way that I did it. And yeah, you'd be done. And that is the last question, guys. So y'all, that ought to do it for this one. This is Mr. Robinson. Thank you so much for watching this Chapter 1 review. And I don't know if this covered everything under the sun that we've done, but it sure did a lot. And I got a lot of exploration on these things, especially when we started talking about comparing surface areas and volumes and things of the sort. So guys, next coming up would be Chapter 1 Test and Cumulative Assessment. A whole nother set of probably 18 or so questions, once again, that we'll have that maybe covers even more of this in a broad way. So take care, and I'll see you probably in that next one.